Hello everyone, this is the lecture over lesson number 5 part 2. In this part we'll continue talking about the concept of acceleration, starting with the law of falling bodies. All objects that are dropped freely, meaning there are no influence on those objects while falling, they undergo the same acceleration, meaning they fall at the same rate. No matter how big they are, or how heavy, massive they are, or light, they will fall at the same rate. That's 9.8 meter per second. This rate, this constant rate of falling is based on falling freely, meaning there is no air resistance or any other forces acting on the object. So if you drop a feather and the hammer, in the absence of air resistance, the feather and the hammer supposed to fall at the same rate, meaning if you drop them from the same height, they will hit the ground at the same time. But of course, in real life, where there is air resistance, heavy objects usually have the ability to displace the air better than lighter objects. Also, objects that have small volume are less susceptible to air resistance than objects with big surface area. So the feather will undergo more resistance by the air than a nail, for example, or a marble ball. If you drop an umbrella, for example, it will undergo more resistance than a penny. Let's see a short video over that. For example, in this video, we are going to drop a feather and a penny from the same height at the same time. We'll do this experiment first with the presence of air resistance. So there will be air resistance acting on the two objects. Let's see what will happen when we drop them from the same height at the same time.
And feather drop simultaneously from the same height. They behave exactly as we'd expect, each falling at a very different rate.
As you can see here in this experiment, the penny fell faster, and this is not because the acceleration due to gravity is different. It's because there is another factor, which is the air resistance. The force exerted by the air resistance on the two objects are not equal. We'll be experiencing more air resistance due to its surface area and due to the fact that it's lighter. Now, what will happen if we do the same experiment but in vacuum, meaning if we evacuate this chamber completely from air or almost completely from air? What will happen to the two objects if they are dropped from the same height at the same time?
The other. But that's only because of the effect of air resistance on the two objects. In a vacuum, a penny, a feather, and any other object will fall at exactly the same rate.
So now vacuum is applied.
With virtually no air remaining inside the glass tube, the penny and feather are now in a vacuum. When the penny and feather are released, we'll witness the law of falling bodies in action. Without the effect of air resistance.
As you notice here, the penny and the feather hit the bottom at the same time, which indicate that they are falling at the same rate, meaning they have the same acceleration downward. Let's see it in slow motion.
In other words, in a vacuum, all bodies, regardless of their weight, will fall at exactly the same rate.
And there you are, they hit the bottom at the same time. Another experiment is on the moon here. One of the astronauts in the Apollo 13 mission did this same experiment where he dropped a feather and the hammer from the same height. Now notice here in the moon there is no air resistance because there is no atmosphere. There is no atmosphere in the moon, so air resistance is not a factor. And let's see what will happen here when he dropped the feather and the hammer. Here you go, as you see, the feather and the hammer hit the ground at the same time. The first one to predict that all objects fall at the same rate was Galileo. Although he could not produce actual vacuum, he theorized that if objects are in free fall, they will fall at the same rate no matter what their mass is. The way he thought about it, if you have a light object like this hammer and a heavy object like this one here, and they are dropped, would they move faster or slower than a heavy object alone? Now, one way to think about it is that the lighter object will impede the motion of the heavier object. So the heavy object alone is supposed to move faster. But at the same time, the lighter object plus the heavy object has more mass than the heavy object alone, so it's supposed to move faster. So this yields unescapable contradiction. So that was basically Galileo's rationale behind his theory. So what is this acceleration due to gravity? As we mentioned, it's 9.8 meters per second per second. What does that value mean? It means that if you drop an object from rest, its initial velocity is 0, as you see here. But its acceleration is not 0. Its acceleration is 9.8 meters per second per second. So after 1 second, its velocity will increase from 0 to 9.8 meters per second. Notice this is the velocity increasing. The acceleration will stay the same. It's 9.8 meters per second downward. And each second, the velocity will be gaining 9.8. So after 2 seconds, it will become 9.8 plus 9.8, which is 19.6. After 3 seconds, it will become 19.6 plus 9.8, which will yield 29.4 meters per second, and so on. Again, this is assuming there is no air resistance. In real life, because of the presence of air resistance, all objects will reach a constant velocity called terminal velocity. And this terminal velocity is determined by the geometry of the object, its mass, and the amount of air or the density of the air present. Okay, let's talk more about the relation between the acceleration vector and the velocity vector. And let's take this example here. So for example, you have this car going at certain speed, and it's 10 kilometers per hour toward the right. And let's say during that time, let's say at exactly 12, the driver stepped on the gas. The velocity will increase. Let's assume that the velocity increased from 10 kilometers per hour to 20 kilometers per hour in 1 second, meaning the clock reading now is 1 second past 12. So this is 1 second past 12, and the velocity has increased from 10 kilometers per hour to 20 kilometers per hour to the right. Let's try to calculate the acceleration during that period. Now, as we know, the acceleration is always equal to the final velocity, v sub f, final velocity, minus the initial velocity, v sub I, divided by the time taken, which is very much the final reading of the clock minus the initial reading of the clock. And you can see here the final velocity is what? From 12 to 1 second past 12, the final velocity is at 1 second past 12, which is 20 kilometers per hour. So this is 20 kilometers per hour, minus the initial velocity, which is 10 kilometers per hour. Remember, the initial velocity is at 12, the final velocity is at 1 second past 12. This is divided by the time taken. The time taken is the final time, which is 1 second past 12, minus the initial time, which is 12. The difference between 1 second past 12 and 12 sharp is 1 second. So the time taken here is 1 second. And this will yield what? This will give you the acceleration value. Let me write it down here. Which will be 20 minus 10, which will give you 10 kilometers per hour per second. So during that period, during this 1 second period, the acceleration was 10 kilometers per hour per second, meaning the velocity increased by 10 kilometers per hour each second. Now let's look at the second. So let's say here, let me use a different font. Let's say now in 1 second, the velocity also increased from 20 to 30 kilometers per hour. So that's 2 seconds past 12. If we started at 12 exactly, this will be 2 seconds past 12. Apply the same equation. Acceleration is the final velocity minus the initial velocity divided by the time taken. And now here the final velocity is what? We are talking about this time period here from 1 second past 12 to 2 seconds past 12. The final velocity is 30 and the initial velocity is 20. And those are in kilometers per hour. divided by the time taken, and the time taken to go from 20 to 30 is the difference between 1 second past 12 and 2 seconds past 12, or 1 second to 2 seconds, which is 1 second. And this will yield also 10 kilometers per hour per second. And notice in both of those cases, the acceleration and the velocity are in the same direction. The acceleration is in the same direction as the velocity, so the car is gaining speed. It went from 10 to 20 to 30. And in both cases, it's gaining 10 kilometers per hour each second. Okay, now let's assume that at 2 seconds past 12 exactly, the driver saw the stop sign and he stepped on the brake so hard that it brought the car to a stop in 1 second. So the car went from velocity of 30 kilometers per hour to the right here to zero velocity, and that's at 3 seconds past 12. So now to find the acceleration, we have to take the final velocity minus the initial velocity over the time taken to go from the initial to the final value. And here the final velocity is what? Notice here the final velocity will be at 3 seconds past 12 and the initial velocity will be at 2 seconds past 12. Now at 3 seconds past 12, what's the velocity of the car? The car came to a stop, so the velocity is 0. So here the final velocity is 0. While the initial velocity, which is the velocity at 2 seconds past 12, was 30 kilometers per hour. So we'll plug 30 here for the initial velocity. And the time taken is again 1 second. And this will yield minus 30 kilometers per hour per second. What does this negative sign indicate? It indicates that the acceleration is in the negative x direction. So if you take the right to be positive x, the left will be negative x. The sign of a vector quantity indicates the direction of that vector. So if we take the right to be positive, then left will be negative. If you take up to be positive, then down will be negative, and so on. So this means that the acceleration is in the negative direction and its magnitude is 30 kilometers per hour per second. So this one here is deceleration. Why? Because the acceleration vector is opposite to the velocity vector, meaning the acceleration is produced by a force that impedes the motion of that object. Now let's look at that more in the discussion exercises. For example, look at this question here, question 1C. It asks you if the ball is accelerating or decelerating in the figure above. So let's assume this baseball player threw the ball upward with initial speed v0. Let's assume the initial speed was 30 meters per second. And it's upward. As you see, the direction is upward. Of course, at the moment he threw it, as soon as it leaves his grip, and right away it will start decelerating because the acceleration due to gravity, g, is acting on it. Now we know g is 9.8 meters per second, or meter per second square, and it's downward. The direction is downward. And now, for the purpose of simplicity, let's take it to be 10 meters per second, just to make the calculations easier. So what will happen to the speed after 1 second? Now since g is acting downward and it's impeding the speed of the object because the acceleration of gravity is opposite to the direction of the motion of the ball is moving upward, the acceleration due to gravity is downward, so it will reduce the speed after 1 second from 30 meters per second to what? To 20. So the velocity will decrease at a rate of 10 meters per second each second. So now this velocity, which is after 1 second of throwing the ball, 20 meters per second. After another second, the same thing will happen. The acceleration due to gravity, which is downward, will decrease the velocity by 10 meters per second. So the velocity will become 10 meters per second. So that's after 2 seconds. Now after 3 seconds, taking off another 10 meters per second, and that's when the ball reaches maximum height. At zero velocity, it will reach its maximum height. Why? Because the ball will start falling down. Now the velocity is 0, but g is still acting on the object. Throughout the whole trip here, g is constant. It's 9.8 meters per second, which we rounded off to 10 meters per second, and it's always acting downward. So now the ball will start falling downward and now it's gaining speed because the motion and the acceleration are in the same direction. So the ball will be accelerating. So v will become 10 meters per second, then 20 meters per second, and then finally after a total of 6 seconds it will be 30 meters per second. In the way down it's gaining 10 meters per second each second. The trip upward, the ball was decelerating, while during the trip downward, the ball is accelerating. Notice again that what will determine acceleration from deceleration is the relation between the direction of the velocity and the direction of the acceleration. If they are opposite to each other, if the two vectors are opposite, then you have deceleration. If the two vectors are in the same direction, they will have the same acceleration. Now let me go ahead and go over some of the questions here in the discussion. Please answer those questions first before you look at the solution. And also, for example, question number 3, it asks about the relation between velocity and acceleration vectors when the object slows down. Remember, when the object slows down, this means deceleration, and as we mentioned earlier, in the case of deceleration, velocity and acceleration vectors will be opposite to each other. So if the velocity is to the right, the acceleration vector will be to the left. If the velocity vector was downward, the acceleration vector will be upward, or vice versa. Like in the case of gravity, when you throw an object upward, the velocity vector will be upward, while the acceleration vector will be downward. Regarding the question over Galileo's alleged experiment, where the story talks about dropping two objects from the top of the Leaning Tower of Pisa, there was a slight difference because one of the objects is 10 times the mass of the other, as the story goes. So the slight difference would be due to the air resistance. Question number 5 regarding to the initial speed and initial acceleration of objects that are dropped from rest. Now, since the ball is dropped from rest, then the initial velocity will be 0. It's dropped from rest. At the moment you drop it, its speed, its velocity is 0. While its acceleration will be the acceleration due to gravity. So as soon as you release it, it's a free-falling object. Free-falling object means the acceleration will be 9.8 meters per second per second. Here, question number 6, notice that you are given a lot of information. Very important is to look for the information that are relevant to the problem. And here the problem is to find average acceleration in meter per second square. Now, to find the acceleration, we need 3 quantities. Those quantities are the final velocity, the initial velocity, and the time taken. Since you are asked to find the acceleration in meter per second square, hence the unit of the velocity has to be meter per second, and the unit of time has to be second, so that we can get the answer in meter per second square. Now, the final velocity will be what? If you read the question carefully, you see that the oil tanker will come to a stop from an initial speed of what? Of 8.3 meters per second. So the 8.3 meters per second is what? Is it the initial or the final velocity? The final velocity will be 0 because it came to a stop. The final status of that oil tanker is 0. It came to a stop. So the final velocity has to be 0. And the initial velocity is the 8.3 meters per second. How about the time taken? Now the time taken will be the time taken to go from 8.3 meters per second to 0, and that's mentioned here. It takes 20 minutes to come to a stop from a top speed of 8.3 meters per second. But 20 minutes is not in seconds, so we have to convert 20 minutes to second by multiplying it by the conversion factor, 60 over 1 minute, and this is multiplication. And this will yield 1200 seconds. Now we can divide the change in the velocity in meter per second by the time taken in seconds, and this will yield 6.9 times 10 to the negative meter per second square, and the negative sign indicates that the direction of the acceleration is opposite to the direction of the velocity, meaning it's decelerating, and that's expected because the oil tanker came to a stop. Notice that the value is very small. It's 6.9 times 10 to the negative 3 meter per second, and this is expected because the oil tanker is huge, it's very massive, it weighs 500,000 tons, so it has a lot of inertia, a lot of resistance, and that's why it takes 20 minutes to bring it to a stop from a speed of 30 km per hour. 30 km per hour is very much like 22 miles per hour. So it takes 20 minutes to bring it from around 22 miles per hour to zero speed. So you can see the acceleration is really small. So you expect very small number, and always ask yourself if the answer makes sense. So 6.9 times 10 to the negative 3, which means 6.9 millimeter per second, is really expected because the oil tanker is accelerating, or in that case decelerating, at very slow rate. A question in the homework, similar to this one here, or a little bit maybe different, is about a sprinter start from rest and is able to achieve a speed of 12 meter per second. So he went from 0 speed to 12 meter per second in 4 seconds. What is the sprinter average acceleration? And 12 meter per second is very close to 27 miles per hour. So actually 1 meter per second is equivalent to around 2.24 miles per hour. So to calculate the acceleration, you'll take the change in the velocity divided by the time taken. Change in the velocity will be the final velocity minus the initial velocity divided by the time taken to go from that initial value to the final value. And then you plug the numbers. The final velocity is 12, the initial velocity is 0 because he started from rest, meaning the initial velocity is 0, divided by the time taken, which is 4 seconds, and this will yield 3 meters per second per second. If you look at some of the questions in the homework, for example, question about when an object accelerates, then there is necessarily change in what? And now notice here, when object accelerates, then it could be change in either speed, direction, or both. If you change either one, this will yield a change in the velocity, because remember, velocity is a vector quantity, and each vector quantity has two components, magnitude and direction. So you can change the velocity by changing either the magnitude, which is the speed, or the direction, or both. And since acceleration is defined as the change in the velocity, it's not only the change in speed or change in direction, it's either one, speed or direction. Then if the object accelerates, then necessarily there is a change in the velocity. Why the answer is not all of these? Because it could be only change in speed or it could be only change in direction. And velocity encompasses both of them. The same thing in question number 4. If the object accelerates in the direction opposite to the motion, this means that the acceleration and the velocity have opposite direction, so we expect the velocity to decrease. Remember, when the velocity vector and the acceleration vector are opposite to each other, it will yield deceleration. The motion will be deceleration, and hence the velocity will decrease. Object on an inclined surface here in question number 5 will also be under the influence of acceleration due to gravity, so the acceleration is constant, ignoring friction and air resistance. And notice here, unit of acceleration has to be unit of length divided by unit of time divided by unit of time, as we explained earlier in part 1 of lesson number 5. In question number 7, if the velocity of a body increases, we are sure that there is acceleration. Now, why is not number C? Why the acceleration of the body increases? Because the acceleration could be constant, as is the case with falling objects. It could be 9.8 meters per second the whole time. Okay, so it's not necessarily an increasing acceleration. It could be constant acceleration. It could be even decreasing acceleration. Question number 8, a freely falling object. Of course, the choice here is going with uniformly increasing velocity. Why is it uniformly increasing velocity? Because the object is falling with a constant acceleration, 9.8 meters per second each second, meaning the velocity is increasing at a constant rate of 9.8 meters per second each second. Each second you are adding 9.8 meters per second to the velocity value. Also, if you look at question number 11, what does it mean to have a constant acceleration of 9.8 meters per second squared? This means basically that the speed or the velocity is increasing at a rate of 9.8 meters per second each second. It's not A, because A actually indicates what? Indicates constant speed. If the object travels at 9.8 meters each second, meaning it's traveling the same distance each second, and that constitutes constant speed. And the same thing, B constitute constant speed or constant velocity. C constitute increasing acceleration, and the acceleration here is not increasing, it's constant acceleration. So the correct answer is D. Also, a question about centripetal acceleration, or what centripetal means. Centripetal means a motion that seeks the center of a circle, usually circular motion or close to circular motion, like the orbit of planets or the orbit of satellites around the Earth, where the direction of the acceleration is always toward the center of that circular motion. And we'll talk about that more in lesson number 6. This brings us to the end of this lesson. Please feel free to ask any questions. Thank you.